Okay, we'll get started. So up on CCLE, I uploaded homework 1. That will be due this Friday at 6 p.m. I've also, yeah, that's pretty much it. Okay, so the homework 1 template's available. You can download it and work through that. This first homework is less programming and more kind of just learning some details about some of the functions. And then, you know, the next assignments will be a little bit more programming heavy, I guess. Okay, and today's lecture is right here. Let's take a look. We are continuing on in our discussion of. Well, I guess. Sure, we'll give you a try, Microsoft Edge. But okay, so here we go. We're continuing on in data structures. And we left off on this slide, I believe, on coercion. We said you throw in a logical vector or something like that, and you throw it into the function sum or mean, and it's going to coerce everything. The trues will get coerced into ones, the falses get coerced into zeros, and then now if you take the mean of a vector of ones and zeros, it's going to just be the proportion that's 1, okay? And this often happens automatically whenever you throw it into some kind of function or operator. So, you know, if you got, you know, addition and subtraction or things like that. And whereas the logical operators, such as the and or, those will get coerce things into logical things, okay? We can also explicitly coerce vectors or items or objects, whatever we want to call them. And for all of these things, I recommend just typing in help logical or help, you know, as.logical, and it will give you some information on how these things work, okay? So generally, when we think of turning things into logicals, we think of ones and zeros, but anything that's other than a 0 will get coerced to true. So you can just test this out on your own computer. You can say, you know, as.logical -4, and that will get coerced to true, okay? As.logical can also coerce character strings, okay? So if you give it the character string true, it will recognize that as true, or if you give it lower, like false, you know, pretty much any variation of these things, those will coerce to true or false. Whereas if you give it a different character string and it can't figure out what to do, it's going to return NA for missing. Okay. Here's a few other ones. As.integer. Okay. As.integer generally. Numeric values will be truncated towards 0. Okay, so if you give it, you know, 3.1415, it's going to just truncate it to 3. Okay, and negative values, again, they also get truncated towards 0. If you you can give it a character string or something, and it will be able to convert it into an integer. And if you if there's a decimal there or white space, it will drop the decimal, it'll drop the white space, okay? However, as.integer, the largest integer value that your computer can hold is pretty much this, okay? This is pretty much the biggest integer value, about 2 billion, something like that, okay? It can't hold integer values, just the way it stores integers in memory. Can't handle it. So if you try to give it a numeric value that's bigger than this, it's going to return this. It's going to return NA, and it will say, warning, NA is introduced by coercion to integer range, saying that the value you tried to give it was outside of the range of integers. Okay, and there's if you type in .capital machine, it will list off information about your computer, okay? Pretty much everybody uses an Intel chip these days. I guess there's a few computers, some of you might have an AMD chip, but pretty much if you have an Apple It's all an Intel chip. Most Windows machines use Intel chips, and so because of that, these are characteristics inherent to the chipset, not anything within the software, but inherent to the chipset that says this is the biggest integer value that we can hold, things like that. So you can ask about your computer and say .machine $integer.max. I suppose if you go on some old computer, I don't know if it will be able to run R, but if it did, you could ask it this question and it might give you something different. Or if you had a different chipset, maybe it's something else. But pretty much your CPUs are all Intel, so okay. So that's as integer. As character does stuff that we might expect it to do, okay? So all it does is it takes the thing and it just puts quotes around it, okay? Or if you give it a number, okay, as.character pi, it will keep about 15 significant digits for if you say something for as.character, okay? So you can try this out on your computer. You can do square root of 2 and ask as.character. If you want to keep more decimals or anything like that, you can use format, okay? This is just so that it doesn't introduce any wrong values by coercing to character, okay? Okay. You can also coerce things to numeric type or type double, okay? And so you have as.numeric, you have as.double. I think there's even an as.single. There's no single data type, single precision floating point decimal data type in R, but I think as.single even exists. But anyway, as.numeric is the same as as.double. And it will just try to coerce things, and pretty much if you give it a number in quotes, it will try to turn it into a number, but it doesn't understand something like this, right? So if you give it English words, it's going to say a missing value. So it'll give you a warning, okay? What's the difference between a warning and an error? I didn't put this in my slides. But yeah.
An error will stop your code from running, or a warning will just maybe give you the output.
Yeah, exactly. So if it's an error and it's in the middle of your code will stop and it will not continue. Okay. A warning, your code will continue, but it will say a warning. Okay. And warnings generally mean I did it, but I'm not sure if this is what you really wanted me to do. Right. So when you say as.double and you give it some text and it turns it into a missing value, the code will keep running. It doesn't stop the code, but it just says, I'm not sure if this is what you wanted because now we've got missing values, right? And so sometimes if you run a loop, it'll run and then it'll come back and it'll say like generated 50 warnings or something like that. And maybe that's happened to you, maybe it hasn't, but something like that. So basically it just means the code ran, but you better check your output, make sure it did what you wanted it to do. Okay, so sometimes when we did coercion, we got these NAs. So NAs are missing values, right? And there are different types of NAs for the different vector types. So if you ask type of NA, it's going to say logical. Why did it do NA logical? Why is the type NA for logical? Okay, well, so think of this. If we had a vector of 1, 2, 3, and they have a missing value, what will happen to that NA? Okay, so let's say I have 1, 2, 3. Okay, what is this? What is this type? This is type of double, right? Okay. If I throw in an NA in here, what's this going to be? This is going to be type of, it's still double, right? The NA, it's originally logical, but it gets coerced into double, right? If I have, if I say type of, and I have a vector true and false, this is logical. I throw in the NA here, it's going to be logical. Okay. There's actually different NA types. You got NA underscore. NA logic. NA, the original NA is logical. So of course we got NA character, NA complex, NA integer. So let's do NA character. Right. So if I feed this into true, false, NA underscore character, what's this going to do? This is the missing value specific for character type, and so it coerces everything into character type. Okay, so we have different NA values. We have the NA for the different data types. Okay, so yeah, we've got an NA for logical. If you you can try to add values to missing things, and it's going to say that's missing. Okay, and if I say what's the type of this thing, this NA, it's now the double type. It's been coerced into type double. So because you can't, in order to add things together, they have to be able to have the same type, right? So we've got NA plus 1 gets coerced into double. Is that all right? Okay, and then, and if you ask, is something NA, right? Let's say you want to know, do I have missing values in my vector? And you want to go, okay, for I and whatever my vector, is NA equal to NA? Well, this is not going to work because is a missing value equal to a missing value? It's not. That's not true. It's just it's missing. It can't compute. The result of this thing, because it's missing, is just missing. Okay. If you want to know is something a missing value, you have to use the function is.na. Okay. So don't mix this up with this. All right. Anything equal to missing is always going to be missing. All right. Yeah. And here you go. If you throw a missing value into a vector 4, 5, 3, and you say what is the type of that thing, it's gonna, or I'm sorry, NA underscore real is type double. That's for real values there. Okay. So that's missing values for NA. On the other hand, we also have null. Okay, null is the null object, and it gets its own type. It's type of null. If you ask what is the type of for null. But it's the only thing that has type of null, okay? We can't, it's not going to do anything, okay? And then to ask is something null, you have to say is dot, you have to use the function is null, okay? If we asked, so if I do 3 equal to NA, that's going to say NA. And if I do 3 equal to null, it returns a logical vector of length 0. Okay, that's what logical 0 means the result is logical, but the length of the vector is a 0 length vector, meaning I've got no values inside my vector. Okay. It's a little weird. Okay, and whereas if you ask is NA on the null object, it returns pretty much a lot of operations that you're expecting true falses for. You throw it on the null object, it's going to be logical 0. Okay, is logical the null object, that's false. Okay, you do operations with the null thing, it returns in this case, integer 0, because the addition coerces the false into type integer. Okay, so it's returning integer 0. Okay, and then if I throw in null into a vector, there's almost like no evidence that that thing was even there. Okay, this is the same as just 4, 5, 3. Okay, so yes.
The length of that vector, was it B3?
It is the length of this vector is 3. Yeah. So if I do, oops, that's not the one. Yeah, for all, yeah, this is. So if I say, let's store this as, yeah, we'll just do length of this thing. What's going on here? Oh, not length. Getting my languages mixed up here. Okay. Length is 3. This is okay. These two are identical. 453 and 45 null 3 are identical. Okay, we have other values, not a number, infinity, and negative infinity. Okay, these are all type doubles. These are inherent to floating point arithmetic, and so these do these things. Okay, we don't always get what we expect. Okay, pi divided by 0 will give infinity. 0 over 0 is not a number. Okay, I mean obviously we're not supposed to divide by 0, but And don't use this as like trying to prove things in math, okay? This is just some machine representation of mathematical concepts. They're not, it's not actually infinity, okay? We didn't actually reach infinity when we did this, okay? Like if you do 10 to the, what is it? 300. Okay. Maybe that. Okay. So 10 to the 900 is not actually equal to infinity. All right. But in the computer's mind, it can't just differentiate between infinity and a very big number. Okay. Yeah. I guess I can just do dot machine. What is it? Double max. Okay, so this is the biggest number the computer can represent. And if I add anything to that, let's say 10 to the 300. Okay, no, it's not big enough. Then it goes to infinity. Okay, so yeah, don't expect this to be like proofs of math, but you can do certain operations in it, and it gives you stuff. Okay. All right. What are we going to get if we do any of this stuff? Okay. So I'm going to combine a missing value plus an integer and the letter C. Well, all right, we'll just go through the answers. Okay, it's kind of hard. All right, so integer divided by 0 and missing. Okay, and then we got integers over here. Integers 1 through 3 and a 5, and then 3 integer missing, not a non-number plus an integer. Okay, because they're all just weird things, right? Okay, so this all gets coerced into characters. The missing value is still missing. Okay. Here we took an integer divided by 0, so that gives us infinity, but it's a missing value, and this is type double. Okay, anytime you have infinity, it's going to be type double. Okay, and these values are integers, but the 5 is double, so it gets coerced to double there. Okay, we got the integer 3, and not a number again is, so the not a number and the infinities are always type doubles. Okay, and so when we ask about those are doubles. And if you try to add not a number to any kind of other value, real or integer or whatever it might be, it just returns a number. Okay. Missing value in true, that's logical. Okay, this is the missing value. NA itself is logical type. All right, let's take a look at vector arithmetic here, and so operators often work element-wise. So if I say 1 through 4 plus 2 through 5, okay, it's going to do 1 plus 2, get 3, 2 plus 3 to give me 5, 3 plus 4 to give me 7, and 4 plus 5 to give me 9. Okay, and the same type of thing with multiplication. 1 times 2 gives me 2, 2 times 3 gives me 6, 3 times 4 gives me 12, and 4 times 5 gives me 20. That's fine. I think you guys are used to this. Okay. This part you may or may not be used to. Okay. If R runs out of one vector, it's going to recycle those elements. Okay. So if I have 1, 2, 3, 4 times 2 and 3, it's going to do 1 times 2, 2 times 3, then it reaches the 3, and then it recycles that 2, 3. So it goes back to 2, and then it goes to 3. So it's going to be 3 times 2, and then 4 times 3. Okay, so you get 2, 6, 6, and 12. It still happens if, even if there's kind of a length mismatch. Okay, you go 1, 2, 3, 4, and then over here we have the vector 2, 3, 4, right? So it's going to go 1 and 2, 2 and 3, 3 and 4, and then when it reaches the end of this vector, it goes back and it recycles, and it starts off at 2. So it goes 4 times 2. And then R goes, hey, wait a second, I didn't finish the second vector. I started at 2, and then I ran out of pieces. So then it kicks back a warning. Okay, it says longer object length is not a multiple of the shorter object length. Okay, so but if you had a length vector of 1 through 6, then it would not complain because it goes 2, 3, 4, 2, 3, 4, and it says, oh, that's perfect. We ended over here and we ended over here at the same time. That seems reasonable, and so it stops. Okay, but if you so it won't give you a warning, but it's entirely possible that's not what you wanted it to do either. So for example, maybe you wanted it to go 2, 2, 3, 3, 4, 4, or something like that. Okay, then this normal rules of recycling, which go element-wise, going 2, 3, 4, 2, 3, 4, is probably not what you wanted. And if you needed to do 2, 2, 3, 3, 4, 4, you have to use you have to create that vector either using repeat or some other function to get what you want. Okay. Okay, so you get a warning there. Okay, now we can talk about lists. Okay, so again, so far we've been talking about atomic vectors. Atomic vectors means all the elements in that vector have to be of the same type. Now we got lists. Lists are still considered vectors in the scope of how R works, but they allow for different types of data types there. Okay, and so here we go. Okay, so here I've got a list, and there are 4 things in my list. Okay, I've got the character A, then I have a logical vector with the elements true, false, then I have a numeric vector, okay, type double with 4 elements in it, and then I have a function in there. Okay, and so we can see there are 4 things in my vector. That's at the kind of the top level to show with a double bracket, meaning shows that I've got 4 things in the vector, in the list, and then and each of these may have 1 or multiple things. So the second object in the list is itself a vector with 2 elements in it, and the third object in the list is a vector with 4 elements in it. Okay, and this is still treated as a one-dimensional object. Okay, so R still sees this as a one-dimensional thing. Okay, and if you ask what is the structure of that list that we created, it's going to say it's a list of 4 things where we've got character, logical, numeric, and then a function, okay? And then it does all of this, okay? Along with some attributes. We can have recursive lists. Lists can also be nested inside of other lists, okay? And so here I've got B, which is a list of 2 elements. Where the 2 elements in list B is a numeric vector of length 1, which has just 1 element, 5, and the second element is, the second object in the list is a numeric vector of length 1 with the number 12. C, oh, I made the mistake of calling it C. We're going to get in trouble later. So the C here is a list with one object, a numeric vector of length 1 with the object 13. Okay? If I combine these into object A, list B and C, here we can see at the top level, and it looks crazy here, okay? At the top level, we've got list object 1 and then list object 2. Within list object 1, I've got the first list object, which is a numeric vector where the first element is a 5, okay? The second object in the first list is a numeric vector of 1 with the value of 12, okay? So this is kind of saying the first object in the second list element. And you can have like deep hierarchical structures in your list, okay? So the structure of A is a list of 2, which is itself comprised, the first object is a list of 2 and the second object is a list of 1. And there we have that. Okay. It gets a little bit messy, but it also works in a logical way. Is this okay? This recursive list stuff? Okay. The behaviors of stuff is a little bit, may or may not be what you expected, okay? So if you use list, I guess it worked out okay using the C here. If we use the function list here to combine a list with a vector, then it lists those, and we've got a recursive thing. We've got list of 2, where the first one is a list of 2 items, and then the vector 3, 4 here, okay? If I use combine on the same elements here, then it's going to kind of coerce everything into list type, and we end up with this thing, okay? We have a list of 4 with 1, 2, 3, and 4, okay? This, I generally recommend against using the combine over lists, just because the behavior is often, it's harder to predict how it's going to behave. Okay. Whereas if you throw everything to list, you know it's going to work as lists and stuff. So, or either that, or unlist the elements and then work with them that way. Okay. With lists, we often will name things to reference the objects in the list. Okay. And you can define the names right there in the list, okay, as you create it, right? And so we've got list, the first item in the list is A, and then B, which itself is a list with objects C and D, and then we've got E, okay? So when we look at the structure of this thing, we've got a list of 3. At the top level, we have A, B, and E, and then within B, we have a list of 2 where it's labeled C and D, okay? And of course the names can be whatever you want them to be, okay? It doesn't have to be this. And then we can reference those objects inside the list using the $ notation, okay, which you're probably familiar with. Okay. Otherwise, you have to use double bracket notation as far as subsetting goes. We'll probably cover subsetting tomorrow. And so we've got the $ notation to reference kind of your first element there. Okay, and then you can ask what is B. I'm just going to do that. If you ask for C directly, it's going to say it's going to return null. Okay, meaning that thing does not exist. It's not a missing value. It's a thing that doesn't exist. You're asking at the top level, what is C? C doesn't exist at the top level, so it returns back null, saying that thing doesn't exist. If you want the thing called C, you have to use $B. B itself is a list, so to reference within the list called B, you use $C. Okay, and then you get back what you want, the 2. Okay, so beyond all of this, we also have attributes, okay? Attributes is just like some additional information that we can attach to any object, okay? So it's pretty much you have this object over here, and then it's like you have a separate sheet of paper or something where you're storing information about each of those objects, okay? And that's, those we can call attributes. Some of the attributes are very important, such as the class and the names and the dimensions of the object, okay? And that's probably going to be your most familiar use of attributes. But attributes can really be anything, and you can access the attributes using either the attributes or attr function. Okay, so for example, if I create a vector with named elements, okay, so x is going to be a vector, okay, and it's going to be a numeric vector, and we're going to give it names L, M, and N, okay, and there we go. The parentheses around everything just means don't just make it, because generally when you use equals or the arrow to assign something, R is not going to print out that object. But if you put parentheses around that thing that you just stored, then it will print out the object that you just created as well. Okay, so that's just what the parentheses here mean. Okay, so here it prints it out, M, L, M, and N. And if we ask what are the attributes now associated with X, it says, oh, we've got names, okay? And the names here are L, M, and N, okay? And we see there's a $, which indicates to us is attributes a list and attributes is a list, okay? So if we ask what is the structure of the object attributes of X, okay, so attributes of X returns whatever the attributes thing is, that we see, okay, it's a list where the only object in there is a names vector with character data in it, okay? And then you can also access the attributes this way by using, tell me the attributes of X that are called names, and it returns the vector element in, okay? But, and so, yes, attributes are stored as a list, and it's just, whatever you want to throw in there, you can throw in there, okay? So we can rename the attributes. We can say we're going to change this thing, attributes names, right? This is just that character vector. If we say, okay, we're going to use the letters 1 through 3, okay, then it renames it, and we ask what is X. Now we can see the names are A, B, and C. Okay, you guys know about the letters vector, right? Lowercase letters vector and capital letters vector. Like if you write all caps letters and lowercase letters, these are just inherent vectors that exist in R, and it's just the letters A through Z. Okay, but so if you just quickly need to call something A through Z, you don't have to type out A, B, and C or something like that. And there's not even a shorthand way to write like A:C or something. But you can reference those just calling the letters vector and then subsetting the letters that you need 1 through 3 using square brackets. Okay, and then again, whatever attribute you want, okay, you can throw it in there. So we can say attributes x, and then we're just making up a new attribute called myAttribute, and I'm just going to store in the phrase this is a vector. And now we ask what are the attributes of x? We have the names, and then this is a vector is now stored in there. So if you want to attach functions and I don't know, whatever else you want to attach to the thing, you can do that. That is allowed. Okay. However, when you modify a vector or whatever, okay, those attributes are often lost. Okay, so you can store these attributes, but then as soon as you change it, you know, a lot of these attributes that you created and attached, those get thrown away. Okay, the only ones that don't get thrown away are names, dimension, and class. Okay, and you can, and because these are so important, they have shortcut functions. So you can just say names of x instead of writing attributes of x, quote names, right? So in the other way, like if I wanted to access this thing, this is a vector, I would have to either do attributes of x, $myAttribute, or attributes x. I'd have to write this, and then it would return back what it is that I put in there, okay? But names, dim, and class, these are shortcuts to those attributes, okay? So just keep in mind that names, dim, and class, this is just attributes. These are just values stored in that list of attributes. Okay, and just like anything else, you can modify these things. So the attributes of x, this is what we have. We've got the names a, b, c, and myAttribute. This is a vector. If I modify x by subsetting it, okay, I say subset x to just the first element, and I ask what is the attributes of that thing. This myAttribute thing that I created is lost, and instead now I just have only the names attribute is preserved. Okay, the other stuff is lost in the process. We can talking about the names, we can name a vector in 3 ways. We can do it when we create it. We can modify the names, okay, by kind of just saying names of x and then throwing it in there, okay? Or you can create kind of another copy, and you can say set names, and then you say using the set names function, okay? Probably this second method is probably going to be your most common method, I think, and that just modifies the vector in place. And of course, you could, quote, modify in place by using set names and then storing it back into x, okay? But technically, that's a copying operation. But in R, you often modify something and then you store it back into its thing, right? A lot of times you do like x is equal to x plus 1 or something like that. What that's doing is it's creating an entirely new value, but then it's storing it in its old location, okay? Names don't have to be unique, all right? But if you're going to do character subsetting, which we'll cover either tomorrow or Friday, unique names are very important, okay? And then it says, not all elements of a vector need to have a name, all right? If some names are missing, names will return an empty string for those elements. And if all names are missing, the names will return null. Let's see. Okay, let me see if I can just give you a quick example here. So we'll do x is 1 through 3, and then we'll do names of x is, so we can ask, what is the names of x? Right now, it's null, right? So we can then do names of x. What will happen if I say letters 1 through 2? So I've got names of x, letters, and we're just going to give it a and b. All right, let's see. So x gets a and b, and then the third element, it just has no name. Okay, so we can ask, what are the names of x? It's going to be a, b, and na now. Okay. This names thing is not a recycling operation, so it's not going to recycle through this vector 1 and 2. Okay, so generally, just your your math operations are recycling. Are operations that do vector recycling. Okay, I'd say most functions don't really do that, okay? But your mathematical operators do. So this is what it's going to get, okay? And we can also just say, I can do names of x. And it will be, we'll do the vector A, NA, and C, okay? And then so if I ask what is x now it says it's that, okay? And then we can reference what is A and what is the thing. Did I do something wrong? X subset. Oh, it's a capital C. Okay, I thought I was going crazy. All right. All right, we got factors. Okay, factors is another quote data type. It's not really a data type. It's but well, it is. Okay, so you create a factor by saying factor, and then you give it some stuff here. Okay, and then it says, okay, we've got A, B, B, and A, and then the levels that it sees are A and B. Factors are inherently stored as integer. So if you say type of, so here x is, we created a factor, x is a factor, and if I say what's the class of x, it's a factor, but if I say type of x, it's an integer, okay? And if we ask what are the levels of x, it's going to return back A and B. So let me just do, so x will be factor A, B, B, and A. Okay, so we got x here. Okay, type of x, and then if I say levels of x, so it's an integer type, and if I do it like as.integer of x, we can see it's actually stored as 1, 2, 2, 1, right? And then notice when we print out x, there's no quotes around A and B. It just prints it out A and B, okay? If I say, what are the attributes of x, okay? It says, it gives me two things. There's levels, and then there's the class factor, okay? So the attributes of x is, a list with 2 elements. If I ask, what's the structure of this thing? Okay, it's a list of 2. We've got levels, and we've got the class, okay? So you can't, with a factor, if you try to throw in a value that's not included in the levels, it's going to kick back a warning here. Okay, it's going to coerce an NA, and it's going to kick back a thing. And you can't combine factors. I can't just say combine factor of A and factor B. It's going to see this, the underlying integer value here is a 1 when you created this factor. And the underlying integer value over here is also a 1 when you created this factor. And so when you do that, we get 1, 1, okay? It says factors are useful if you already know kind of the values you're expecting to see, okay? So here, if we have 3 observations of m's here, and we create a table, it's just going to say, I see 3 m's here, okay? If we throw this into a factor and we say we're going to expect to see m's and f's, then maybe an x or something, you get 3 and 0, and that is produced when you create a table on the factor. Okay, so even if certain values are not observed, if they exist in the levels, then they will appear in the when you create a table of something of that nature. Okay, a lot of times when we import data using something like read.csv or even data frame, okay, so when we create data frames later, those the default nature is to treat characters as factors, okay, and then so there's something called stringsAsFactors, and or something will unexpectedly turn into a factor, right? You've got a whole bunch of values, numbers, 3, 5, 7, but somehow when you bring them into R, when you import it, suddenly that column is a factor. What's going on? A lot of times you'll have a missing value in that column. Maybe it's encoded as a dash or encoded as something that R doesn't recognize as a missing value, but it sees it as a character string, okay? And as soon as one thing is identified as character, then the entire thing will get coerced into strings, and then R's default nature is to treat a column of string or character values as a factor, okay? And so everything gets turned into a factor. So what you want to do is you'll probably want to use the argument na.strings, which says whenever you see this string object in the thing, treat this as a missing value, okay? And again, the default nature is to treat strings as factors, and a lot of times this is not what we want to do, okay? A lot of times we want the string information to be left as strings, and so we would use stringsAsFactors equals false. There might have been a time back in the day when you were doing experiments and you would call something like treatment 1 or treatment 2, and those truly were factors where you had different levels of something and they had different names. In that case, it makes sense to leave it as a factor, but you can always import everything as strings and then go back and change those specific columns to factors. But if you turn everything into a factor, then it just gets messy, right? It says factors often look like character vectors, and we have all of this stuff. But you know, if you want to do anything where you expect the things to behave like strings, you should leave them or explicitly coerce them into strings, or just leave them as strings. Okay, it looks like we're about to run out of time here. Okay, so before we get into the two-dimensional or multi-dimensional stuff on matrices and arrays, I guess we'll end here. So we'll end talking about factors and lists and all of that. Go ahead and you can start taking a look at your homework assignment. Again, that's due Friday, and so it shouldn't be too bad, okay? So we'll stop here and we'll see you guys on Wednesday.